and we'll solve the fourth problem for Gauss's law. So let me write the question first. This is the fourth one. And it's basically the following. There is an infinitely long, obviously it's not really infinite, it's very, very long, it's just an approximation, solid cylinder with a uniform and non-conducting and a uniform charge density of rho. So let me write it here, a non-conducting and uniform charge density of rho. Okay? And so this is a three-dimensional distribution of charge. It's uniform and it's non-conducting, meaning that the charges are not moving, they're kind of stationary. And we're asked to find out for this cylinder, non-conducting, very long cylinder, like a cable or something. Okay, so the figure looks like the following. So let me draw it. I think here it would be a good idea. Let me draw it with this. And so it's something like this. Okay, and the radius of this, let's say cable, is capital R, and the charge density is given as rho. Okay, and we are asked to find out the electric field for two different cases. So find out the magnitude of the electric field, and this is a function of rho, r, and small r. Okay, so what is this? So that is the question. Okay, so we will look at two different cases. The first one is going to be calculate this for the case of, let me use the pink color. So part A. So calculate that when small r is smaller than capital R, meaning that find out the electric field inside this uniformly distributed charge density, and let's say positive charge density, and somewhere inside this cable. So what is the electric field? And the idea is we're going to use the Gauss's law. First, what we will do is we will select a good, in quotations, Gaussian surface, a nice one. And what we mean by nice Gaussian surface is we will choose Gaussian surface so that we can take the electric field out of the integral so that we don't have to do the integral. So that was the idea, as you remember last time. Okay, so for the first case, how would it look like, the Gaussian surface? So let me draw on this, actually. Let's try to do that. So what we will do is we will take a Gaussian surface, let's say something like that, okay? And where the center of this Gaussian surface, which is also a cylinder, will coincide with the central axis of the cable itself. Okay, so this is the Gaussian surface. And you will see in a short while why this is a nice Gaussian surface. And Gauss's integral is the following. So EdA, closed surface integral EdA, is equal to Q enclosed for this Gaussian surface divided by epsilon 0. And the idea is the following. There are three different surfaces here, right? And these are, let me give even labels here. So let's call this surface A1. Let's call the other surface. So this is like the top of, let's say the bottom of this cylinder, and let's say this is the top of the cylinder if you put it like that. And the A3 is the side part of the cylinder. Okay, so I'm going to call that A3. So this part, I'm going to call it A3. Okay, so this integral is basically has two parts. So this is a closed integral which is composed of all the total closed Gaussian surface, and I can basically take it apart and express that in terms of these three parts, right? So meaning E times dA for A1 plus E times dA for A2 and E times dA for A3, right? So there are 3 parts. Okay, so the top part, say top, and bottom, and side. Okay, and from the figure, let me draw it with this the other color. So you see the electric field. This is a very long cable, and we know that the electric field, if it's positive, is going to go like exactly like this, right? And on this A2 and A1, you can see that the electric fields go up, but the vector's direction for A2 as well as A1 is normal to the surface. So this is the direction of A2. Let's call it A2 with a hat, and this is A1 hat. So that's like normal to the surface. And this is the direction of A3 vector. And these are electric fields, right? Both here and here. And same thing happens in here. This is like the side part, and all of these parts, A3 is perpendicular or normal to the surface. So here you can see that for A1 and A2, the electric field and the area vectors, they're actually perpendicular to each other. But as you know, the Gauss's integrals contribute if and only if they're along the same direction. So this is, or at least one component is along the same direction. So since this is a scalar product, because A1 is perpendicular to E, this is 0. So is this one, because A2 is perpendicular to E, but this guy is not, right? So this is along the same direction. So what I can do is, for this guy, I can actually take, this is a nice Gaussian surface, because wherever you are, you're exactly r away from the central axis, and it's completely symmetric. Due to symmetry, the magnitude of your does not depend on dA, so you can simply take it out, and dot product gives you 1 because they're along the same direction. It's cosine of 0, which is 1. So all of these things are going to give you the following. So let me write it here. So all of that green, maybe blue. So this is going to give you E, the magnitude of that times for the third surface dA, okay? And that is equal to Q enclosed divided by epsilon 0. So let me call that equation number 1, okay? And E, I can write it, and I can, so you see this integral, as you can see, so this is dA of A3, and if you add all these small dAs, you're going to get the whole A3, right? So this integral will give you A3, and therefore E is equal to Q enclosed divided by A3 times epsilon 0, right? Okay, so we now know what the magnitude is, but we're missing 2 things, right? What is Q enclosed and what is A3? One of them is easy. We know what A3 is. A3 is basically the area of the side part, which is the circumference multiplied by the length. So that's 2 pi r times the length, right? And how about Q enclosed? Q enclosed is equal to, it's the volume charge density here, it's the uniform volume charge density rho, multiplied by the enclosed volume, the pink one, for this cylinder, right? And what is the enclosed volume? It is a cylinder, and therefore it is the area of the cross-section multiplied by the length, right? So it's pi r squared multiplied by the height of the cylinder. In this case, it's L, right? Okay, so if we substitute these guys in here in this equation, the magnitude of E is going to be Q enclosed, which is rho times pi r squared times L, right? That's Q enclosed, all divided by the area, which is 2 pi r times L, and there's an epsilon 0 here. So there's a nice cancellation here. You see that pi's cancel, 1 of the square gets, this got canceled, and L's cancel as well. So let me use 2 of these so that you will distinguish the 2. Okay, so if you make these cancellations, there is rho on top, and r squared now is r. And on the bottom, I have 2 left, and there's this constant epsilon 0. Okay? So let's take it into a box. It's rho r divided by 2 epsilon 0. Okay? So this is the magnitude of the electric field for the case of r smaller than capital R. Now, the second part is B. Okay, And the second part is when radius r, small r, is bigger than capital R, meaning that maybe it's a good idea to redraw it. Let's say this is the cable. It's a very long cable again. It goes like that from both sides. And the radius is capital R. Now we are interested in a point where it is away from capital R. So now the Gaussian surface, so it is now small r away from capital R, but now this time R is bigger than capital R. So the Gaussian surface for this is going to be again a cylinder, but this time it's going to be a cylinder which will include the original cable inside. And again, it will be like that, right? The length of the cylinder is again L. Okay, now it's again the same idea. This is A1, this is A2, and the side part is A3. All of these things are exactly the same. So the magnitude of the electric field is again, let me write it here so that you will remember. The magnitude of that is equal to Q enclosed divided by A3 multiplied by epsilon 0. So everything is the same. Now the different thing is the A3 is still the side part, right? It's still 2 pi r, so that didn't change. 2 pi r, the circumference multiplied by the length. That's like the area of the side part. Now the thing that is different is now Q enclosed is, it is rho times, now the enclosed charged volume is not the whole thing. It's not pi r square r. It just is the cable's charge, right? So which is going to be just this part. Inside the pink one, it's just the green one where the cable is located, right? So therefore, now this volume, enclosed volume, is not pi times r squared where r is small, it's actually pi times capital R squared times L. Because there's no charge outside of this cable, right? So that's why the volume that matters, which we are going to multiply by the rho, is just pi times capital R squared, which is the radius of the cable itself. So that's why if you put these guys into this equation, electric field, the magnitude of that, when R is bigger than R, will be Q enclosed is rho pi times R squared times L, right? And we are going to divide that to A3, and A3 is 2 pi small r, again, times L times epsilon 0. Again, there are some cancellations, as you can see. This pi goes away, and L goes away, and we are left with the following. So let me write down the final equation in here. Therefore, the magnitude of the electric field when R is bigger than capital R is equal to rho R squared divided by 2 times R times epsilon 0. And let me put it in a box. And there's a nice, correspondence between the two. As you can see, when small r is equal to capital R, these two should basically be equal to each other, and it is actually, right? Because this R squared and there's R here. When I make the substitution of R goes to capital R, both of these should agree, and they do, right? Because then I'm going to have R squared divided by R, and they're going to cancel, and now this is capital R, and they agree with each other. Okay, thanks for listening.